These are the energy graphs that we did together in class. The piece of clay is falling, so its gravitational potential energy is falling, right? Height is directly related to how much gravitational potential energy something has. So we get this smaller and smaller bar, and then no bar at all once it's landed on the ground. Our kinetic energy bar is connected to how big our velocity arrow is. So no velocity arrow here, the piece of clay is just being dropped. Then velocity arrow means we've got some EK. And then by the end, we don't have any EK again because there's no velocity arrow. This is actually seeing as it hits the ground. So that's why we have this descending EGP bar. We only have EK for the middle area. And then once it's splatted on the ground, all that energy must have gone somewhere because the total energy can't have changed. So we say that it turns into heat and sound. And that's what our pie graphs look like as well. Remember, E total is not on our pie graphs because it is the whole pie. So we just have the 1 and then this 2 split up for each of these. These two are both GP and EK. These two are heat and sound because the object has stopped. Similarly, down here, we started with a ball rolling along the floor. So it started with a lot of kinetic energy. And you could say that it had a little bit of heat and sound, but I'm okay with this if you put all kinetic energy here, all 8 of our energies. All of our total is kinetic. The ball's rolling. As the ball rolls, it slows down. We can tell because the velocity vector gets smaller. So this EK has now turned into some heat and sound. It's generated heat and sound. One thing I'm going to nitpick is that all of these bars need to add up to this 8. So 3 plus 3 plus 2 is 8 total bars. Now, another thing I'm going to nitpick is that the heat and sound bars cannot get smaller. That heat and sound has already been created. It cannot turn back into another kind of energy. So by the time this rolls to a stop, and we have no EK anymore, no velocity vector, we have only EH and ES. And we need to split that based on what we do here. So this is 1, 2, 3, 4, 5 versus 3. So it's like 3/8. Quick way to do 8s is just to split, 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 split. So 3 of the 8s, all of this is E sound. And then we can say the rest is E heat. Pause or rewind this if you need more. So on the back, we've got the object being thrown up in the air. Now this needs to show a big velocity vector at first. It says place the velocity vectors on the dots. Big velocity vector at first. And then as it rises, it slows down, as we know that a ball would do. At the top, it stops. Now you could technically say it has a very small amount of sideways kinetic energy, but if the ball is just being thrown straight up and falls straight back down, then we just can't represent that with a two-dimensional picture, right? It would be up and down and be very confusing. So we're not going to say this has any kinetic energy. This is all EGP at this point. Then on the way back down, we have a very different situation. How big should I make this arrow? Well, if we think about how much EGP it has less than here, but more than here, which means it has more kinetic energy than this one and less than this one. So our arrow needs to be in between these two sizes. Something like this. And I don't care about the size of the I just care about the relative difference. This should be the smallest, and then this one should be the same size as this one. Because what ball we throw up with a speed comes back down to that height with the same speed. Now, why don't we put this all as kinetic energy? Well, because it's still a little bit off the ground. So we're going to say some pie slice here, I'm not picking on how big it is exactly, is EGP. And the rest is our EK. For this one, it should be about the same ratio almost, but most of it is now going to be EGP. A very small amount of it is EK because our velocity vector is very small. A large amount of it is EGP because our height is very large. Height is connected to EGP, speed is connected to EK. So then it reaches the top, it's all EGP. Now on the way back down, we've got this in between. In fact, this is about halfway down. So about half of it should be EGP. That matters. If you see something easy like half, well, let's go half and half. Different than this, it must be different. And then here, it actually should look exactly the same as this one over here, because it's at the same level. So there's my EGP, making it the same, and my kinetic energy, EK. So then for the ball on a coiled spring, when it's launched upwards, when it's here, does it have any velocity? No. How do I know? No arrow. So is it off the ground? Yes, I would say a little bit off the ground. I'm going to give it a little bit of EGP, about the equivalent to where it is here, about 2 clicks. I'm going to say that my E total is 8, and I can immediately draw that 8 all the way across, because E total doesn't change. So what's the rest of my energy? It has no kinetic, it hasn't made any sound, but this E elastic is this new one that we've talked about just a little bit, but it's whenever there's elasticity in a spring. So how much must there be? Well, it has to add up to 8, so 6 of it must be E elastic. And then it bounces off the spring. No more E elastic, right? I didn't even put it down here. EGP, however, has grown, right? It's now further away from the ground. So I'm going to draw this up to a level rather equivalent with being that much higher. I'm going to say I take it up to 1, 2, 3, 4, 5. And again, all of my bars need to add up to my total. So my EK, well, first I have to decide, is there any heat or E sound? I would argue, no, there's not either one. Some people have said, well, a spring makes a little bit of sound. If you want to do 1 dot of sound here, you just have to do 1 less dot of EK. But I'm going to say that this just has these two, EK and EGP. 1, 2, 3, 4, 5, 6, 7, 8, 8 here. Now it's reached the top of the arc. No kinetic energy. If it created any sound when it boinged the spring, you'll want to put that here as well. But if you didn't, like I didn't, then this is just all EGP. Now for modeling the truck. It's just come down a hill and now it's rolling uphill without using gasoline. So it has kinetic energy to start. And I did mess this up. This arrow needs to be smaller and this arrow needs to be gone. Use bar graphs or pie graphs to represent the energies present. What's important here, no matter which method you choose, I'll use pie graphs just arbitrarily, is that my totals need to be the same size. So I actually messed this one up a little bit. The total size of the circle needs to be the same because the total amount of energy doesn't change. And then at the beginning, it's all EK. Halfway up, it's half EGP, half EK. And by the top, it is now all EGP. So that's the crucial idea. We're just looking at how much energy it has. Size matters. Size of the pie graph matters. Size of the bar graph matters. Size of the velocity vector matters.